The cathode ray tube is a vacuum tube containing one or more electron guns and a fluorescent screen used to view images. It has a means to accelerate and deflect the electron beam, S, onto the screen to create the images. The images may represent electrical waveforms, pictures, radar targets or others. CRTs have also been used as memory devices, in which case the visible light emitted from the fluorescent material is not intended to have significant meaning to a visual observer. The CRT uses an evacuated glass envelope which is large, deep, fairly heavy, and relatively fragile. As a matter of safety, the face is typically made of thick lead glass so as to be highly shatter-resistant and to block most X-ray emissions, particularly if the CRT is used in a consumer product. CRTs have largely been superseded by newer display technologies such as LCD, plasma display, and OLED, which have lower manufacturing costs, power consumption, weight and bulk. The vacuum level inside the tube is high vacuum on the order of 0.01 pascals to 133 nPa. In television sets and computer monitors, the entire front area of the tube is scanned repetitively and systematically in a fixed pattern called a raster. An image is produced by controlling the intensity of each of the 3 electron beams, one for each additive primary color with a video signal as a reference. In all modern CRT monitors and televisions, the beams are bent by magnetic deflection, a varying magnetic field generated by coils and driven by electronic circuits around the neck of the tube, although electrostatic deflection is commonly used in oscilloscopes, a type of diagnostic instrument. History. The experimentation of cathode rays is largely accredited to J. Thomson, an English physicist who, in his 3 famous experiments, was able to deflect cathode rays, a fundamental function of the modern CRT. The earliest version of the CRT was invented by the German physicist Ferdinand Braun in 1897 and is also known as the Braun tube. It was a cold cathode diode, a modification of the Crookes tube with a phosphor-coated screen. In 1907, Russian scientist Boris Rosing used a CRT in the receiving end of an experimental video signal to form a picture. He managed to display simple geometric shapes onto the screen, which marked the first time that CRT technology was used for what is now known as television. The first cathode ray tube to use a hot cathode was developed by John B. Johnson and Harry Weiner Weinhardt of Western Electric, and became a commercial product in 1922. It was named by inventor Vladimir K. Zworykin in 1929. RCA was granted a trademark for the term in 1932. It voluntarily released the term to the public domain in 1950. The first commercially made electronic television sets with cathode ray tubes were manufactured by Telefunken in Germany in 1934. Oscilloscope CRTs. In oscilloscope CRTs, electrostatic deflection is used, rather than the magnetic deflection commonly used with television and other large CRTs. The beam is deflected horizontally by applying an electric field between a pair of plates to its left and right, and vertically by applying an electric field to plates above and below. Oscilloscopes use electrostatic rather than magnetic deflection because the inductive reactance of the magnetic coils would limit the frequency response of the instrument. Phosphor persistence. Various phosphors are available depending upon the needs of the measurement or display application. The brightness, color, and persistence of the illumination depends upon the type of phosphor used on the CRT screen. Phosphors are available with persistences ranging from less than 1 microsecond to several seconds. For visual observation of brief transient events, a long persistence phosphor may be desirable. For events which are fast and repetitive, or high frequency, a short persistence phosphor is generally preferable. Microchannel plate. When displaying fast one-shot events, the electron beam must deflect very quickly, with few electrons impinging on the screen, leading to a faint or invisible image on the display. Oscilloscope CRTs designed for very fast signals can give a brighter display by passing the electron beam through a microchannel plate just before it reaches the screen. Through the phenomenon of secondary emission, this plate multiplies the number of electrons reaching the phosphor screen, giving a significant improvement in writing rate and improved sensitivity and spot size as well. Graticules. Most oscilloscopes have a graticule as part of the visual display, to facilitate measurements. The graticule may be permanently marked inside the face of the CRT, or it may be a transparent external plate made of glass or acrylic plastic. An internal graticule eliminates parallax error, but cannot be changed to accommodate different types of measurements. Oscilloscopes commonly provide a means for the graticule to be illuminated from the side, which improves its visibility. Image storage tubes. These are found in analog phosphor storage oscilloscopes. These are distinct from digital storage oscilloscopes which rely on solid-state digital memory to store the image. Where a single brief event is monitored by an oscilloscope, such an event will be displayed by a conventional tube only while it actually occurs. The use of a long-persistence phosphor may allow the image to be observed after the event, but only for a few seconds at best. This limitation can be overcome by the use of a direct-view storage cathode ray tube. A storage tube will continue to display the event after it has occurred until such time as it is erased. A storage tube is similar to a conventional tube except that it is equipped with a metal grid coated with a dielectric layer located immediately behind the phosphor screen. An externally applied voltage to the mesh initially ensures that the whole mesh is at a constant potential. This mesh is constantly exposed to a low-velocity electron beam from a flood gun which operates independently of the main gun. This flood gun is not deflected like the main gun but constantly illuminates the whole of the storage mesh. The initial charge on the storage mesh is such as to repel the electrons from the flood gun which are prevented from striking the phosphor screen. When the main electron gun writes an image to the screen, the energy in the main beam is sufficient to create a potential relief on the storage mesh. The areas where this relief is created no longer repel the electrons from the flood gun which now pass through the mesh and illuminate the phosphor screen. Consequently, the image that was briefly traced out by the main gun continues to be displayed after it has occurred. The image can be erased by resupplying the external voltage to the mesh restoring its constant potential. The time for which the image can be displayed was limited because, in practice, the flood gun slowly neutralizes the charge on the storage mesh. One way of allowing the image to be retained for longer is temporarily to turn off the flood gun. It is then possible for the image to be retained for several days. The majority of storage tubes allow for a lower voltage to be applied to the storage mesh which slowly restores the initial charge state. By varying this voltage a variable persistence is obtained. Turning off the flood gun and the voltage supply to the storage mesh allows such a tube to operate as a conventional oscilloscope tube. Data storage tubes. Color CRTs. Color tubes use three different phosphors which emit red, green, and blue light respectively. They are packed together in stripes or clusters called triads. Color CRTs have three electron guns, one for each primary color, arranged either in a straight line or in an equilateral triangular configuration. A grill or mask absorbs the electrons that would otherwise hit the wrong phosphor. A shadow mask tube uses a metal plate with tiny holes, placed so that the electron beam only illuminates the correct phosphors on the face of the tube. The holes are tapered so that the electrons that strike the inside of any hole will be reflected back, if they are not absorbed, instead of bouncing through the hole to strike a random spot on the screen. Another type of color CRT uses an aperture grill of tension vertical wires to achieve the same result. Convergence and purity in color CRTs. Due to limitations in the dimensional precision with which CRTs can be manufactured economically, it has not been practically possible to build color CRTs in which three electron beams could be aligned to hit phosphors of respective color in acceptable coordination, solely on the basis of the geometric configuration of the electron gun axes and gun aperture positions, shadow mask apertures, etc. The shadow mask ensures that one beam will only hit spot certain colors of phosphors, but minute variations in physical alignment of the internal parts among individual CRTs will cause variations in the exact alignment of the beams through the shadow mask, allowing some electrons from, for example, the red beam to hit, say, blue phosphors, unless some individual compensation is made for the variance among individual tubes. Color convergence and color purity are two aspects of this single problem. Firstly, for correct color rendering it is necessary that regardless of where the beams are deflected on the screen, they hit the same spot on the shadow mask. This is called convergence. More specifically, the convergence at the center of the screen is called static convergence, and the convergence over the rest of the screen area is called dynamic convergence. The beams may converge at the center of the screen and yet stray from each other as they are deflected toward the edges. Such a CRT would be said to have good static convergence but poor dynamic convergence. Secondly, each beam must only strike the phosphors of the color it is intended to strike and no others. This is called purity. Like convergence, there is static purity and dynamic purity, with the same meanings of static and dynamic as for convergence. Convergence and purity are distinct parameters. A CRT could have good purity but poor convergence, or vice versa. Poor convergence causes color shadows, or ghosts along displayed edges and contours, as if the image on the screen were entirely printed with poor registration. Poor purity causes objects on the screen to appear off-color while their edges remain sharp. Purity and convergence problems can occur at the same time, in the same or different areas of the screen or both over the whole screen, and either uniformly or to greater or lesser degrees over different parts of the screen. The solution to the static convergence and purity problems is a set of color alignment magnets installed around the neck of the CRT. These movable weak permanent magnets are usually mounted on the back end of the deflection yoke assembly and are set at the factory to compensate for any static purity and convergence errors that are intrinsic to the unadjusted tube. Typically there are 2 or 3 pairs of 2 magnets in the form of rings made of plastic impregnated with a magnetic material, with their magnetic fields parallel to the planes of the magnets, which are perpendicular to the electron gun axis. Each pair of magnetic rings forms a single effective magnet whose field vector can be fully and freely adjusted. By rotating a pair of magnets relative to each other, their relative field alignment can be varied, adjusting the effective field strength of the pair. By rotating a pair of magnets together, preserving the relative angle between them, the direction of their collective magnetic field can be varied. Overall, adjusting all of the convergence purity magnets allows a finely tuned slight electron beam deflection and all lateral offset to be applied, which compensates for minor static convergence and purity errors intrinsic to the uncalibrated tube. Once set, these magnets are usually glued in place, but normally they can be freed and readjusted in the field if necessary. On some CRTs, additional fixed adjustable magnets are added for dynamic convergence and/or dynamic purity at specific points on the screen, typically near the corners or edges. Further adjustment of dynamic convergence and purity typically cannot be done passively, but requires active compensation circuits. Dynamic color convergence and purity are one of the main reasons why until late in their history, CRTs were long-necked and had biaxially curved faces. These geometric design characteristics are necessary for intrinsic passive dynamic color convergence and purity. Only starting around the 1990s did sophisticated active dynamic convergence compensation circuits become available that made short-necked and flat-faced CRTs workable. These active compensation circuits use the deflection yoke to finely adjust beam deflection according to the beam target location. The same techniques also make possible the adjustment of display image rotation, skew, and other complex rastered geometry parameters through electronics under user control. Degaussing: if the shadow mask becomes magnetized, its magnetic field deflects the electron beams passing through it, causing color purity distortion as the beams bend through the mask holes and hit some phosphors of a color other than that which they are intended to strike. For example, some electrons from the red beam may hit blue phosphors, giving pure red parts of the image a magenta tint. This effect is localized to a specific area of the screen if the magnetization of the shadow mask is localized. Therefore, it is important that the shadow mask is unmagnetized. Most color CRT displays, that is television sets and computer monitors, each have a built-in degaussing circuit, the primary component of which is a degaussing coil which is mounted around the perimeter of the CRT face inside the bezel. Upon power-up of the CRT display, the degaussing circuit produces a brief, alternating current through the degaussing coil which smoothly decays in strength to zero over a period of a few seconds, producing a decaying alternating magnetic field from the coil. This degaussing field is strong enough to remove shadow mask magnetization in most cases. In unusual cases of strong magnetization where the internal degaussing field is not sufficient, the shadow mask may be degaussed externally with a stronger portable degausser or demagnetizer. However, an excessively strong magnetic field, whether alternating or constant, may mechanically deform the shadow mask, causing a permanent color distortion on the display which looks very similar to a magnetization effect. The degaussing circuit is often built of a thermoelectric device containing a small ceramic heating element and a positive thermal coefficient resistor, connected directly to the switched AC power line with the resistor in series with the degaussing coil. When the power is switched on, the heating element heats the PTC resistor, increasing its resistance to a point where degaussing current is minimal, but not actually zero. In older CRT displays, this low-level current is sustained along with the action of the heating element as long as the display remains switched on. To repeat a degaussing cycle, the CRT display must be switched off and left off for at least several seconds to reset the degaussing circuit by allowing the PTC resistor to cool to the ambient temperature. Switching the display off and immediately back on will result in a weak degaussing cycle or effectively no degaussing cycle. This simple design is effective and cheap to build, but it wastes some power continuously. Later models, especially Energy Star rated ones, use a relay to switch the entire degaussing circuit on and off, so that the degaussing circuit uses energy only when it is functionally active and needed. The relay design also enables degaussing on user demand through the unit's run panel controls, without switching the unit off and on again. This relay can often be heard clicking off at the end of the degaussing cycle a few seconds after the monitor is turned on, and off during a manually initiated degaussing cycle. Vector monitors. Vector monitors were used in early computer-aided design systems and in some late 1970s to mid-1980s arcade games such as Asteroids. They draw graphics point-to-point, rather than scanning a raster. Either monochrome or color CRTs can be used in vector displays, and the essential principles of CRT design and operation are the same for either type of display. The main difference is in the beam deflection patterns in circuits. CRT resolution, dot pitch defines the maximum resolution of the display, assuming delta gun CRTs. In these, as the scanned resolution approaches the dot pitch resolution, more copyright appears, as the detail being displayed is finer than what the shadow mask can render. Aperture grille monitors do not suffer from vertical Moira copyright. However, because their phosphor stripes have no vertical detail. In smaller CRTs, these strips maintain position by themselves, but larger aperture grille CRTs require one or two crosswise support strips. Gamma CRTs have a pronounced triode characteristic, which results in significant gamma. Other types of CRTs, cat's eye. In better quality tube radio sets, a tuning guide consisting of a phosphor tube was used to aid the tuning adjustment. This was also known as a magic eye, or tuning eye. Tuning would be adjusted until the width of a radial shadow was minimized. This was used instead of a more expensive electromechanical meter, which later came to be used on higher-end tuners when transistor sets lacked the high voltage required to drive the device. The same type of device was used with tape recorders as a recording level meter. Charactrons, some displays for early computers used charactron CRTs. These incorporate a perforated metal character mask, which shapes a wide electron beam to form a character on the screen. The system selects a character on the mask using one set of deflection circuits, but that causes the extruded beam to be aimed off-axis, so a second set of deflection plates has to re-aim the beams so it is headed towards the center of the screen. A third set of plates places the character wherever required. The beam is unblanked briefly to draw the character at that position. Graphics could be drawn by selecting the position on the mask corresponding to the code for a space, which had a small round hole in the center. This effectively disabled the character mask, and the system reverted to regular vector behavior. Charactrons had exceptionally long necks, because of the need for 3 deflection systems. NIMO. NIMO was the trademark of a family of small specialized CRTs manufactured by industrial electronics engineers. These had 10 electron guns which produced electron beams in the form of digits in a manner similar to that of the charactron. The tubes were either simple single-digit displays or more complex 4- or 6-digit displays produced by means of a suitable magnetic deflection system. Having little of the complexities of a standard CRT, the tube required a relatively simple driving circuit, and as the image was projected on the glass face, it provided a much wider viewing angle than competitive types. Williams tube. The Williams tube or Williams-Kilburn tube was a cathode ray tube used to electronically store binary data. It was used in computers of the 1940s as a random access digital storage device. In contrast to other CRTs in this article, the Williams tube was not a display device, and in fact could not be viewed since a metal plate covered its screen. Zeus thin CRT display. In the late 1990s and early 2000s, Philips Research Laboratories experimented with a type of thin CRT known as the Zeus display, which contains CRT-like functionality in a flat panel display. The devices were demonstrated but never marketed. The future of CRT technology, demise. Although a mainstay of display technology for decades, CRT-based computer monitors and televisions constitute a dead technology. The demand for CRT screens has dropped precipitously since 2000, and this fall-off had accelerated in the latter half of that decade. The rapid advances and falling prices of LCD flat panel technology, first for computer monitors and then for televisions, has been the key factor in the demise of competing display technologies such as CRT, rear projection, and plasma display. The end of most high-end CRT production by around 2010 means an erosion of the CRT's capability. In Canada and the United States, the sale and production of high-end CRT TVs in these markets had all but ended by 2007. Just a couple of years later, inexpensive combo CRT TVs have disappeared from discount stores. It has been common to replace CRT-based televisions and monitors in as little as €5 or 6 years, although they generally are capable of satisfactory performance for a much longer time. Companies are responding to this trend. Electronics retailers such as Best Buy have been steadily reducing store spaces for CRTs. In 2005, Sony announced that they would stop the production of CRT computer displays. Samsung did not introduce any CRT models for the 2008 model year at the 2008 Consumer Electronics Show, and on February 4, 2008 Samsung removed their 30 inches widescreen CRTs from their North American website and has not replaced them with new models. The demise of CRT, however, has been happening more slowly in the developing world. According to iSupply, production in units of CRTs was not surpassed by LCD's production until 4Q 2007, owing largely to CRT production at factories in China. In the United Kingdom, DSG, the largest retailer of domestic electronic equipment, reported that CRT models made up 80–90% of the volume of televisions sold at Christmas 2004 and 15–20% a year later, and that they were expected to be less than 5% at the end of 2006. Dixon ceased selling CRT televisions in 2007. Causes: CRTs, despite recent advances, have remained relatively heavy and bulky and take up a lot of space in comparison to other display technologies. CRT screens have much deeper cabinets compared to flat panels and rear projection displays for a given screen size, and so it becomes impractical to have CRTs larger than 40 inches. The court disadvantages became especially significant in light of rapid technological advancements in LCD and plasma flat panels, which allow them to easily surpass 40 inches as well as being thin and wall-mountable, two key features that were increasingly being demanded by consumers. By 2006, although the price points of CRTs were generally much lower than LCD and plasma flat panels, large-screen CRTs were as expensive as a similar-sized LCD. Slimmer court: some court manufacturers, Both LG Display and Samsung Display have innovated CRT technology by creating a slimmer tube. Slimmer quart has a trade name SuperSlim and UltraSlim. A 21-inch flat quart has 447.2 mm depth. The depth of SuperSlim is 352 mm and UltraSlim is 295.7 mm. Resurgence in specialized markets. In the first quarter of 2008, CRTs retook the number 2 technology position in North America from plasma, due to the decline and consolidation of plasma display manufacturers. Display Search has reported that although in the 4Q of 2007 LCDs surpassed CRTs in worldwide sales, CRTs then outsold LCDs in the 1Q of 2008. CRTs are useful for displaying photos with high pixels per unit area and correct color balance. LCDs, as currently the most common flat-screen technology, have generally inferior color rendition due to the fluorescent lights commonly used as a backlight. CRTs are still popular in the printing and broadcasting industries as well as in the professional video, photography, and graphics fields due to their greater color fidelity, contrast, and better viewing from off-axis. CRTs also still find adherence in video gaming because of their higher resolution per initial cost, lowest possible input lag, fast response time, and multiple native resolutions. CRT monitors are still widely used in the study of the brain's visual processing. The speed and fidelity of their response, combined with the simplicity of their design, makes them well suited for experiments where scientists need to have very fine control over stimuli which are presented to an observer. Health concerns. Ionizing radiation. CRTs can emit a small amount of X-ray radiation as a result of the electron beam's bombardment of the shadow mask aperture grille and phosphors. The amount of radiation escaping the front of the monitor is widely considered unharmful. The Food and Drug Administration regulations in 21 CFR 1020.10 are used to strictly limit, for instance, television receivers to 0.5 milliroentgens per hour or 36 picoampere per kilogram, at a distance of 5 cm from any external surface. Since 2007, most CRTs have emissions that fall well below this limit. Toxicity. Older color and monochrome CRTs may contain toxic substances, such as cadmium, in the phosphors. The rear glass tube of modern CRTs may be made from leaded glass, which represent an environmental hazard if disposed of improperly. By the time personal computers were produced, glass in the front panel used barium rather than lead, though the rear of the CRT was still produced from leaded glass. Monochrome CRTs typically do not contain enough leaded glass to fail EPA TCLP tests. While the TCLP process grinds the glass into fine particles in order to expose them to weak acids to test for leachate, intact CRT glass does not leach. In October 2001, the United States Environmental Protection Agency created rules stating that CRTs must be brought to special recycling facilities. In November 2002, the EPA began finning companies that disposed of CRTs through landfills or incineration. Regulatory agencies, local and statewide, monitor the disposal of CRTs and other computer equipment. In Europe, disposal of CRT televisions and monitors is covered by the WEEE directive. Flicker. At low refresh rates, the periodic scanning of the display may produce an irritating flicker that some people perceive more easily than others, especially when viewed with peripheral vision. Flicker is commonly associated with CRT as most televisions run at 50 Hz or 60 Hz, although there are some 100 Hz PAL televisions that are flicker-free. Typically only low-end monitors run at such low frequencies, with most computer monitors supporting at least 75 Hz and high-end monitors capable of 100 Hz or more to eliminate any perception of flicker. Non-computer CRTs or CRT for sonar or radar may have long persistence phosphor and are thus flicker-free. If the persistence is too long on a video display, moving images will be blurred. High-frequency audible noise. 50 Hz per 60 Hz CRTs used for television operate with horizontal scanning frequencies of 15,734 Hz or 15,625 Hz. These frequencies are at the upper range of human hearing and are inaudible to many people. However, some people will perceive a high-pitched tone near an operating television CRT. The sound is due to magnetostriction in the magnetic core and periodic movement of windings of the flyback transformer. This problem does not occur on 100-120 Hz TVs and on non-CGA computer displays, because they are working on much higher frequencies compared to the low-frequency noise of mains hum. Implosion, high vacuum inside glass-walled cathode ray tubes permits electron beams to fly freely without colliding into molecules of air or other gas. If the glass is damaged, atmospheric pressure can collapse the vacuum tube into dangerous fragments which accelerate inward and then spray at high speed in all directions. The implosion energy is proportional to the evacuated volume of the CRT. Although modern cathode ray tubes used in televisions and computer displays have epoxy-bonded faceplates or other measures to prevent shattering of the envelope, CRTs must be handled carefully to avoid personal injury. Security concerns. Under some circumstances, the signal radiated from the electron guns, scanning circuitry, and associated wiring of a CRT can be captured remotely and used to reconstruct what is shown on the CRT using a process called Van Eyck freaking. Special tempest shielding can mitigate this effect. Such radiation of a potentially exploitable signal, however, occurs also with other display technologies and with electronics in general. Recycling. As electronic waste, CRTs are considered one of the hardest types to recycle. CRTs have relatively high concentration of lead and phosphors, both of which are necessary for the display. There are several companies in the United States that charge a small fee to collect CRTs, then subsidize their labor by selling the harvested copper, wire, and printed circuit boards. The United States Environmental Protection Agency includes discarded CRT monitors in its category of hazardous household waste, but considers CRTs that have been set aside for testing to be commodities if they are not discarded, speculatively accumulated, or left unprotected from weather and other damage. Leaded quart glass is sold to be remelted into other CRTs, or even broken down and used in road construction. Advantages and disadvantages. Pros: high contrast ratio, excellent color, fairly wide color gamut and low black level. No native resolution. The only current display technology capable of true multisyncing. The image is continuous in one dimension and discrete in only one dimension, unlike competing display technologies like LCD and plasma displays that are discrete in both dimensions since they have screens with fixed permanently defined pixels. The continuous nature of CRT scan lines means there is no need for interpolation on a line, and lines can be scaled ideally with no loss of quality simply by linear amplification of the beam deflection signal in the primary scan direction. No input lag. No ghosting and smearing artifacts during fast motion due to sub-millisecond response time, and impulse-based operation. Near zero color, saturation, contrast or brightness distortion. Excellent viewing angle. Allows the use of light guns pens. Can be used or stored in both extreme hot and cold temperature conditions without harm to the system. Cons: large size and weight, especially for bigger screens. Unit weighs about 50 lb. Geometric distortion caused by variable beam travel distances. High power consumption. On average, a CRT monitor consumes €2.10, the power that an identically sized LCD monitor would consume, depending on the type of backlight used in the LCD screen, and its brightness setting. A lot of heat can be emitted during operation, due to relatively high power consumption. Can suffer screen burn-in, though not as quickly as plasma displays. Produces noticeable flicker at refresh rates lower than 85 Hz. Hazardous to repair service without proper training and precautions taken. Maximum size for direct view displays is limited to about 40 inches due to practical and manufacturing restrictions, though the sizing can be increased with an array of separate displays, such as the original Jumbotron used at sports arenas. The glass envelopes contains toxic lead and barium as X-ray radiation shielding. The phosphors can also contain toxic elements such as cadmium. Many countries treat CRTs as toxic waste and prohibit their disposal in landfills or by incineration. Purity and convergence in color tubes, affected by the Earth's magnetic field, usually roughly factory preset for operation in either the northern hemisphere, the southern hemisphere, or the equatorial area, but may require trimming at final location. Adjustment at final location requires a high degree of technical skill, as well as safety precautions associated with opening the display housing. Sensitive to magnetic interference, which can cause the image to shimmer or the colors to shift. Image edges are slightly diffuse, compared to the razor-sharp stationary image an LCD, PDP, or other screen with fixed predefined pixels can produce. For text displays, computer-generated diagrams and line drawing, and other images composed mostly of sharp edges, razor-sharp pixel definition is often preferred. However, this may be seen as an advantage for continuous tone images such as photographic television, as it yields more natural images with no pixelation and it introduces a natural anti-aliasing effect to image information that is pixelated by its origin. A holo may appear around bright objects on a mostly dark screen. See also. References. Selected patents, U.S. Patent 1,691,324 Zworykin Television System, external links, the Cathode Ray Tube site, PCTECH Guide, Cathode Ray Tubes, CRTs at the Virtual Valve Museum, Samuel M. Goldwasser TV and Monitor Court Information.